You know, in physics, we're obsessed with measuring things. But here's the catch. Not all measurements are the same. Some are super simple, just a number. But others? They're totally useless unless you know which way they're going. That's what we're diving into today. The big difference between scalars and vectors.
All right, let me start with a little riddle for you. How can you run 400 meters, that's a whole lap around a track, a real workout, and still have gone absolutely nowhere? Think about it. The answer is kind of wild, and it's the perfect key to unlocking what we're talking about today.
So here's what's on deck. First, we'll look at the two big ways we measure things. Then, we'll get into scalars, the simple stuff. After that, we'll meet their cooler, more complicated cousins, vectors. We'll have a little showdown between them, and then wrap up with why this whole thing really matters.
Okay, let's get into it. Everything really boils down to this one simple split. You've got your basic measurements on one side, and on the other, you've got these measurements that carry this extra piece of info, an extra layer that totally changes the game.
And this is that big divide we're talking about. On one side, all you need is a number, right? Just the size of something, what we call its magnitude. But on the other side, that number is only half the picture. You absolutely have to know its direction too, or the information is pretty much worthless.
All right, let's start with the easy one. Let's talk about scalars. This is the world where it's all about the numbers, plain and simple.
So, what is a scalar? It's basically any measurement where all you need is the number. That's it. You say the number and you've told the whole story. No need to worry about which way or what direction. And trust me, you use these things constantly without even thinking about it. Your weight, how much time has passed, the temperature. Like, if I say it's 30 degrees out, you wouldn't ask me 30 degrees in which direction, right? That sounds crazy. The question itself doesn't make any sense. And it's the same for stuff like distance or volume.
And you know what's great about scalars? The math is just easy. It's the simple arithmetic we all learned in school. If you have 2 liters of water and you add 3 more, you're always going to have 5 liters. No tricks, no surprises. It's beautifully simple.
Okay, but now it's time to step into the other world, the world of vectors. And this is where things get really cool, because in this world, asking which way isn't just an option, it's everything.
So a vector is needier than a scalar. It demands 2 things to be understood. You need its magnitude, that's the how much part, and you need its direction, the which way part. If you're missing either one of those, you don't have the full story. It's an incomplete thought.
Think about things like force or velocity. Imagine you're a pilot. If air traffic control just tells you your speed is 500 kilometers per hour, that's not enough, right? Are you going north, south? Knowing that direction is literally the difference between landing where you're supposed to and, well, not. It's that important.
So how do we even draw these things? Well, we've got a brilliant little system for that. We use arrows. It's actually perfect when you think about it. The length of the arrow tells you the magnitude, so a bigger force gets a longer arrow. And the pointy end, the arrowhead, just points you in the right direction. Simple, elegant, and it works.
All right, time for the main event. Let's put these 2 ideas in the ring for the classic showdown that makes everything click. In this corner, we have distance, and in the other, displacement. Okay, get this image in your head. You're standing at the starting line of a running track. The gun goes off, you run a full, complete lap, 400 meters, and you end up right back where you started. You're tired, you're sweaty, you definitely moved 400 meters. Or did you? And boom! Here's the answer to that riddle from the beginning. The distance you traveled, that's our scalar, is absolutely 400 meters. That's how much track your feet actually covered. But your displacement, that's our vector, is a big fat 0. Why? Because displacement only cares about the straight line from your start point to your end point. And since your start and end points are the exact same spot, you haven't been displaced at all. You literally went nowhere. Okay, so this is a neat trick, but why does it actually matter? Who cares? Well, you should, because this difference completely rewrites the rules of math when you're dealing with how things interact in the real world, especially when you're talking about forces. And this is the big takeaway. You cannot, I repeat, cannot just add vectors together like they're numbers. It doesn't work that way. That direction part we keep talking about, it forces you to play by a whole new set of rules.
Let's make this super simple. Imagine you and a friend are pushing a big box. If you both push on the same side in the same direction with 10 newtons of force each, your forces add up. You get 20 newtons of force, and that box is going to move. But what if you push on opposite sides? You're pushing with 10 newtons, your friend is pushing with 10 newtons, they completely cancel each other out. The total force is 0, and the box goes nowhere. That is vector addition in a nutshell.
So there you have it, the huge difference between just a number and a number that knows where it's going.
And believe me, this isn't just some boring textbook concept. This is the actual language that governs all motion in the universe. Which really makes you think, doesn't it? How does this simple idea, this system of arrows, guide everything from the GPS in your pocket to the complex path of a rocket shooting for another planet?